Every NLP paper written after 2012 assumes you know what a neural network is. Every job description says familiarity with deep learning. Every explainer starts with, a neural network learns representations from data, and most people watching still don't have a mental picture of what the thing actually is. It's a stack of matrix multiplications with squishy functions in between. That is it. That's the whole trick. Welcome to Lecture 6, 10 videos on how deep learning ate NLP. And I want to start by handing you the 90-second version of a neural network. Not the intuition, not the metaphor about brains, the literal thing. Because once you see the shape, every paper for the next 10 videos gets 10 times easier to read. Lecture 5 ended with embeddings. Every word became a dense 300-dimensional vector. Great, but a vector by itself does nothing. You need something to read that vector. Something that can take king as a 300-dim input and figure out enthus is a person, this is male, this is a ruler, this refers to power. That something is a neural network. The puzzle for today. If a neural network is just a stack of matrix multiplications, why is everyone in the field acting like it's magic? Answer: because when you make the stack wide enough and deep enough and train it on enough text, the middle of the stack develops representations that nobody explicitly programmed. That's the surprise. That's what happened after 2012. Today's 3 beats. First, the 90-second neural network. What the thing actually does from input to output with no metaphors. Second, how it learns. Because the input-output shape is only half the story. The other half is how the weights change until it's good. Third, the Lecture 6 roadmap. 10 videos on how deep learning built up to GPT and what actually changed at each step. Beat 1. The 90-second network. Start with an input, say, a 300-dimensional word embedding. That's just a list of 300 numbers. Multiply it by a matrix. Call it WONE. This gives you a new list of numbers, maybe 500 of them, depending on how wide you make the matrix. That's layer 1. Now apply a nonlinearity, element-wise. Most common one is called ReLU. For every number in the vector, if it's negative, set it to 0. If it's positive, keep it. That's it. That's the whole squishing. The reason you need this, without it, stacking matrices does nothing. 2 matrix multiplies collapse into 1. You'd have a fancy calculator, not a network. Now stack it. Another matrix multiply. Another ReLU. Repeat as many times as you want. At the end, one more matrix multiply gets you the output. Say, a probability distribution over your vocabulary. That's a neural network. Matrix, squish, matrix, squish, matrix. Every architecture we cover for the next 9 videos is a variation on that theme. Beat 2. How it learns. Because the shape is trivial. The interesting part is, where do the numbers in those matrices come from? Start with random values. Feed in an input, get an output. Compare to the correct answer, get a loss number. How wrong were you? Then update every weight in every matrix a tiny bit, in the direction that would have made the loss smaller. The nudge in the right direction step has a fancy name, backpropagation. But the algorithm is calculus you might remember from high school, chain rule. If the loss went up because W3 was too big, and W3 was too big because W2 was too big, walk that chain backwards through the network to figure out how much every weight contributed to the error. Then move each weight the opposite way, a tiny bit. Do that trillions of times. Really, trillions, with modern GPUs. And the weights slowly settle into values that make good predictions. Nobody chose them. Nobody knows what most of them mean. But collectively, the stack learns to map inputs to outputs in a way that generalizes. That is the entire trick. And it's why deep learning ate NLP. Beat 3. The Lecture 6 roadmap. Video 2. The 3 godfathers. Hinton, Bengio, LeCun. The trio who kept the deep learning candle lit through the AI winter. Video 3. RNNs. The first serious attempt to make a network read a sequence of words. Almost worked. Not quite. Video 4. LSTMs. The engineering fix that made RNNs actually usable. Video 5. Attention is all you need. The 2017 paper that killed RNNs and lit the fuse for GPT. Video 6. how transformers actually work, no math required. The picture that finally makes it click. Video 7, BERT versus GPT. 2 ways of pre-training a transformer. 2 different paths that both worked. Video 8, the scaling hypothesis. Why bigger models trained on more data just kept getting better, and nobody knows exactly why it works. Video 9, tokenization inside an LLM. We covered BPE in Lecture 3, now we look at it running live inside GPT. Video 10, recap. And then Lecture 7 starts the core NLP tasks: translation, sentiment, named entity recognition, all powered by what we build in these 10 videos. 3 takeaways before the quiz. 1. A neural network is a stack of matrix multiplies with nonlinearities in between. Matmul, squish, matmul, squish. That is the whole architecture. Every fancy model, RNN, LSTM, transformer, GPT, is a variation on that theme. 2. Learning is a loop. Forward pass, compute a loss, run backprop to figure out which weights cause the error. Nudge them, repeat trillions of times. 3. Lecture 6 walks 10 videos of how this simple idea scaled into GPT, godfathers, RNNs, LSTMs, attention, transformers, BERT versus GPT, scaling, tokenization, recap. Quiz 1. What is the shape of a neural network in one sentence? A. A brain simulator with neurons and synapses. B. A stack of matrix multiplies with element-wise nonlinearities in between. C. A decision tree with millions of branches. Or D. A giant lookup table. B. Matmul. Squish. Matmul. Squish. That is literally the whole architecture. The neurons and synapses metaphor is a historical artifact from 1958 that misleads more than it teaches. Just call it a stack of linear layers with ReLU between them. Quiz 2. Why do you need the nonlinearity between matrix multiplies? A. To make it look more like a brain. B. Without it, stacking matrices is equivalent to a single matrix. No expressive power gain. C. To slow down training. Or D. To reduce memory usage. B. This is the reason deep networks can be deep. 2 matrix multiplies with nothing between them collapse into a single matrix multiply, which means a 100-layer linear network has the same expressive power as a 1-layer linear network. The nonlinearity is what makes depth actually add capacity. Quiz 3. What does backpropagation do? A. Runs the network in reverse to generate text. B. Uses the chain rule to compute how much each weight contributed to the error, so we can nudge every weight. C. Randomly shuffles weights to explore the loss landscape. Or D. Copies weights from one layer to another. B. Rumelhart, Hinton, and Williams 1986. Chain rule from calculus, applied backwards through the network. It's the reason we can train networks with millions or billions of parameters. Before backprop, nobody had a scalable way to do this. Back to the puzzle. Lecture 6 is the story of how a very simple idea, stack matmuls, add a squish, learn the weights with backprop, became the engine underneath every LLM. And the whole story rests on that one shape. Next video, the 3 godfathers who kept this idea alive through 20 years of nobody caring. Next time, Hinton, Bengio, LeCun, the trio who won the 2018 Turing Award for keeping deep learning alive when everyone had given up on it. The story of the AI winter, and how 3 stubborn people got us out of it. Hit subscribe.